Okay, so as Steve mentioned, I have recently co-authored an introduction to the field. So this tutorial today, or these two talks, will, at least the first one, will basically be me rushing through this introduction. Okay, parts of it. So at some point, I may, not give the proper credits, forget to say who proved what or what the reference is, but then you can always just go to this paper and you will find the proper references and the proper, yeah. And yeah, so it's been up online for a while, and it's also gone through peer review, and I'm going to make a few edits to the typos, and then we will put the final one up online in a couple of weeks. But this one is already in pretty good shape. Yep. So let's start. So I'm assuming that you'll have seen persistent homology, right? So we are fairly well known with the standard pipeline. We take data, and we associate that data filtration, and then to that filtration we apply homology, and then in the end we get barcodes. Okay. We also seen that yesterday quite a few times. So a couple examples of filtrations. So the first one is the sublevel filtration that I will consider both as a function from x to r, so x is some topological space, but also from x to rn. So they will be defined in exactly the same way with this s and this up arrow. So we take as input this function, and at t, you just consider all the points in the topological space that have a function value less or equal to t. Okay, this is just normal sublevel filtration. So here you can see a nice filtration of the torus. And as a special case of this, we have the offset filtration, where what's being filtered is this dx function, where it's a filtration of a plane, and the filtration is simply take a bunch of points in the plane, and now for any other point in the plane, its function value is its distance to the closest point in your point set. So if you now take the sublevel filtration over that function dx, you will get the standard check filtration that you've seen 100 times, I'm sure, with all these disks growing. And ultimately, we also have the RIPS construction. I don't want to define the RIPS filtration. I'm assuming you've seen it, but you just build a neighborhood graph for increasing radii, and then you take the biggest possible simplicial complex on that graph, and that will give you the RIPS complex. The reason I mention this is because we are going to consider generalization. Okay. So again, input filtration, and then we apply homology, and then out we get the barcode. So if you have like a circular data set like on the slide, then we get one long bar because there are some dots in the middle here that seem to lie in a circle. Okay, but now again, I'm assuming this is fairly well known. Now, I am assuming that this is fairly well known as well, but it connects so much with the second part of my talk. So I really wanted to just, reiterate this. Because now if you go to at least the earlier papers on persistent homology and you try to figure out how do I compute this barcode, well, then you know that there's this inclusion-exclusion formula. Okay, so how do I find the multiplicity of a given bar? Well, first I introduce this beta ij, which is just the rank between the vector spaces hp of xi and hp of xj. And then first you take all the bars that are, all the features, so to say, that are alive at index I, that are alive at index j-1, but they die at ij. So they die when you go from I to j. So these will be like all the bars that are alive at I, but they vanish when you enter j. So that would be all the bars that have like right endpoint up opening full j. And then you subtract all the bars that were alive before I. And you take that difference, you get exactly the multiplicity of ij in the barcode. Okay, fairly well-known stuff, but we will generalize this quite a bit. Okay, so then if you have this filtration here, then you apply this and you get the barcode written here, or you get equivalent to the persistence diagram, where you just take an interval and you plot it, AB is the end points of the bar in the barcode, and you plot the corresponding point in the plane. Okay. So now that was the, the rank invariant, or just computing rank approach of finding the barcode. What we can do is we can also look at the algebra. This is where I've been doing most of my research on the algebra side, multiparameter persistence. But in one case, as Claudia mentioned yesterday, things behave very nicely. So there's a theorem that says that, okay, let's for simplicity just assume that now the vector spaces are indexed by the integers. So I have a sequence of vector space and linear maps, so one vector space for every integer. Then as long as all the vector spaces are finite dimensional, the persistence module, that object decomposes into a direct sum of indecomposables, where each indecomposable is this interval module. So that means that it has it's from an interval from A to B. So you just put the underlying field on every index inside your interval, and you connect them with identity maps. And then you get this so-called concept module or interval module. And as long as your bigger module is PFD, then it decomposes into a direct sum of these interval modules. Okay, this also holds if your indexing category is not only the integers, but any totally ordered sets. It's still the same result. Okay, so what does this mean for those here that may not be so algebraically inclined? It just means that if you compute homology, like if you do it here, for instance, let's say you take this filtration here, and then at index 7, there's an H1 born. Okay, so then let me choose as a base element for index 7 just to be, well, I don't have much of a choice here. And then at index 8, I'm going to choose this cycle as my basis element. Now, if you do that, you will observe that the base element at 7 and the base element at 8, they both map to the same element at index 9. So you have now K, because there's a one-dimensional homology group, and then you have two-dimensional here, and then you go to K again, but now the map is 1, 1 here. And that's not what we want, because we would like to separate the features into these indecomposable components. But what this theorem tells us, that I can always change the basis locally such that everything diagonalizes. Okay, so now I can update the basis in the middle here. Essentially, I can replace this basis element with this other one that goes on the top. And then I get that the first basis element goes to the first basis element, goes to the first basis element. Now 0 goes, well, doesn't really go to anything, but then I have the K and it goes to 0. So I split off the two features into two components. And the theorem just tells you can always choose bases locally such that a basis element always maps to 0 or to a unique basis element. So like this pair. Okay. So that's the intuition here. All right. So persistent homology is great because it's stable. We argue that everywhere. Like you choose persistent homology because it's stable. So if you take a data set and you perturb it a little bit, then you know that the perturbation of the persistence diagram will be bounded. Like the difference between the points in the persistence diagram will be bounded by the amount of perturbation. Okay. I will make that explicit here, what I mean. So I would like to include this slide because there will be a corresponding slide later in multiparameter setting. So here, the Hausdorff distance is simply, so you have two sets. Let's say that, again, they're embedded in some larger metric space. And then if I would like to compute the distance between them, well, I take the point in the one set and I take the point as large as possible distance to any point in the other set. And I record that number, and then I go to the other point, the other set, and I find the point there as largest possible distance from a point in the first set, and I record that distance, and I take the max of those two, and I get the Hausdorff distance. Like it's a common way of measuring distance between a subset of a common metric space. Of course, you can also take a Gromov-Hausdorff distance where the two metric spaces are not assumed to sit inside a larger metric space. But the construction is more or less the same. You just embed them in all possible metric spaces. Okay, but what does persistent homology stability theorem now tell us? Well, it tells us that if I take any topological space and I have two functions on the topological space, and I compute homology in, let's say, dimension I, then the bottleneck distance, so it's like how far apart these points are in the persistence diagram, is bounded by the infinity norm between two functions. Okay. So that's if you take the sublevel filtration, and in particular, you can phrase this in terms of the Hausdorff distance. If you take now the offset filtration, which just you take the, let's say, point in Euclidean space, and you take the union of disks. Now you take one point set and then take another point set. They do not have the same cardinality, but the distance between two point sets is measured in the Hausdorff distance, well, the bond-like distance will be bounded again by the Hausdorff distance. And if you go to something that's not in Euclidean space, but just arbitrary finite metric spaces, then you can bound their bond-like distances of the Rips complexes by the Gromov-Hausdorff distance. Okay, so everything is great, perfect. So we go and we self-persistent homology as the ultimate tool. But now the problem is that it's great stability-wise, but it's extremely sensitive to outliers, right? So if I take my data here, let's say that this is like a really high density region and has some outliers, just hanging around. This is quite common when you do measurements. I mean, it's not. I have never seen a scientific data set where the data look like this, right? And typically looks, well, it doesn't even look like this. It looks much worse. But let's say that we had something like this, and now you run the persistence computation on the figure A, you get this beautiful long bar. But now you run the same computation on the picture B here, and then you see, well, it's hard to decipher the underlying topological signal. Okay, so what can you do? You can say, all right, that's no problem. I will just take all my data points that have a local density at point like above a certain threshold. But then you're somehow breaking with the philosophy of persistent homology, in my opinion, because we like persistent homology because it's really parameter free. We consider all scales because we have learned that you shouldn't just fix one epsilon because then your result will be very sensitive in that epsilon. So now I could choose a density parameter, but then it's going to be very sensitive in that density parameter as well. Okay. So the idea of multi-parameter persistence is to filter your data, to analyze data like this in a way that's scale-free, let's say both in the radius and the density parameter. So what you could do here is that you can take, this is of course a cartoon figure, but you take your data, and then in one direction, you just increase the radius like normal. And in the other direction, you keep adding in points where the points with the highest density appear first, and then lower and lower and lower density, for instance. That's one possible bifiltration. I will show one which is a little bit more concrete soon. But what happens in this case is that basically the algebra looks the same, up until now at least. So you take this one, and you apply, let's say, homology in dimension 0. So what do you find? Well, you find that you have a two-dimensional homology group here, you have a three-dimensional homology group here, and then the linear map just sends the first base element to the first base element, the second base element to the second base element. And if you run through like all the algebra here, we're doing H0 homology, you will see that you get a commutative diagram of vector spaces like this. All right, so you just do multi-parameter persistence like in the 1D case, and you see what happens. Yeah, so I mentioned I should mention one a bit more concrete bifiltration, which is using this is the degree Rips bifiltration, where so this is now so the problem with this one, so I'm trying to sell you something that should be parameter free, but at the same time I'm asking you to estimate the density, but you're not going to estimate the density without choosing any parameters, right? But here's something that's really parameter free, and that's the degree Rips bifiltration. So over here to the right, you will just see the normal Rips filtration of a simplicial complex. The data points that increase the distance thresholds, and then you keep connecting more and more points. But to the left here, we are going to take the restriction to only the points that have a degree a certain number. Okay. So for instance, here I say I'm only going to consider the points that have a degree of at least 2. So if you're the first row here now, well, there are no points because none of the points are connected to anything. There are no degree 2 points here. But if I go to this level, well, this point is connected to 2 points, this to 2 points, and then I'm left with this square here. And then as you go up, you will now ultimately, I think everything will be connected to at least 2 points. There will be no difference between the different columns. And then, of course, you go one more to the left here, and then it will be degree 4. Now, of course, this is just for simplicity. There will be a degree 3, a degree 1, a degree 5, etc., etc. So this is a degree Rips bifiltration. Now, of course, the degree of a point should be a proxy for its density. Right? So a higher degree means that you are surrounded by many points. Okay, good. All right, so we have data. Constructing a multifiltration, well, I can give you many examples. It's not very hard. Applying homology is also not very hard. But then the question is, where do we go next? Right? I want to, compute barcodes. Because most of the things we do in 1D is based on the barcode. So how can we take that theory and put it into that multi-parameter landscape? So Claudia mentioned something yesterday in her talk about quivers, they're wild, etc. So let us just start with a good result. Well, good to some extent. And it tells us that if you are in the multi-parameter setting, then you still have this decomposition result. So you take now a, well, you can take any pole set for that matter, and you have vector spaces connected by linear maps, such that every square here commutes. And as long as all the vector spaces are finite dimensional, your overarching big object M here will decompose into a direct sum of indecomposable modules in a way that's essentially unique. Okay. So the first part we somehow need to prove, but the second part follows from the Grüller-Schmidt theorem, because you also prove that this so-called endomorphism ring is local here, and then 2 is immediate. Okay, so that's great. So then we can just take multi-parameter persistence. We can just compute this decomposition, and then we can use that in our data analysis. Okay, so I was thinking about that for quite a few years. The problem is that there's this wildness here. And to give you an idea what wildness means, let's consider the 5-star quiver. It's like the simplest possible wild quiver. And you put a vector space in the middle, and then you have 5 arrows coming into that middle. And then you ask, how many ways can I construct an indecomposable module here? Okay. So I'm going to make it even simpler. I'm going to assume that the dimension of all the tips here are n. These dimensions, they all have dimension n, and in the middle have dimension 2n. And they'll have the matrices A, B, E, D, C. I don't remember why the order, it doesn't matter. So now the first thing we're going to observe is that if I have something from the 5-star quiver, I can very easily embed that into a multi-parameter persistence module. Because what I do is I take the terminal object here and just put it on the diagonal, connected by like a bunch of identity morphisms. And then if there's an A here, it comes here, and the B, and the C, and the D, and the E. Okay. So if I have something that's indecomposable here, it's definitely going to be indecomposable over here. So to prove that, it's not very hard to see. So the complexity of what happens down here in the 5x5 grid is as least as hard as the complexity over here. So how can I give you a sense of complexity? Well, I can tell you it's wild, you have all these 2-parameter families, etc. But if you look at work by Kutz, going back, I think 60 years or something, he took quivers and he proved that you could actually construct a polynomial. So the number of indecomposables is a polynomial, and you can compute the degree of that polynomial. It's quite easy, actually. Reading the proof is, to me, impossible, I think, for many other mathematicians as well. But extracting the core results is not so hard. So from this quiver here, you can use a dimension vector to compute the Euler form, and then you will see the number of indecomposables of this one with these dimension vectors, like these dimensions, is q to the power of m plus n squared. Okay, so q is now you have a field CQ, and n is this n on the tips here. Okay, so we see that the number of this should be read isomorphism classes. The number of isomorphism classes in the composables goes up pretty quickly here. Okay, and like if you take the normal persistent homology approach, we know that the indecomposables will always look the same independent of this n and this q, because you always just get the intervals as long as you keep it close as this. Okay. All right.
Sorry, Magnus. There was something I don't understand. So we're seeing, what is the variable here? When you say that it's the polynomial with respect to which parameter, to n? Because this is exponentially.
Oh, sorry. Yeah, this is okay. So it's a polynomial in Q of degree 1 plus. Okay. Sorry, yeah, it's a polynomial in Q of degree 1 plus n squared.
So the degree is 1 plus n squared.
Yeah.
Q to the 1.
Yeah, sorry. Yes. Yes. Sorry. So degree is 1 plus n squared, and actually he proved many beautiful things. And if you look at the absolutely indecomposables instead, a little bit stronger, but they're more or less the same amount of them, he proved that it's actually a monic polynomial in Q of degree 1 plus n squared. So now you can actually, this is a fun problem. I would like to understand this better. It's like for a given quiver, you can compute this polynomial, and there's a recursive formula for doing it, but it's very involved. There's a paper that they do it for it. 3 points and 4 arrows and stuff. And the computer ran for a day. Okay. Anyways. All right, so now you may think, all right, so we have this algebraic complexity, whatever that means. Model representation type means basically we don't know how to parameterize the decomposables in any reasonable way. So you may say, well, that's fine because that's just what the algebraics do. Maybe for us in TDA and topology, it doesn't matter. But the thing is that you can construct any multi-parameter persistence module by just gluing together circles in a simple way. So for instance, if I start with this object over here where it has 0, k, so this is in the composable module, you cannot change the basis anywhere here, such that it splits up. So now you would like to represent this one by gluing together circles, and you can do this in a fairly simple manner, as I've done to the left here by just putting well, a circle at this k when this one appears, a circle here when that k appears, and then 2 k's in the middle, and then they somehow die in 3 different ways. So in one way, the feature vanishes because it's, or I guess in 2 different ways. So here that feature gets filled in, but then here another feature vanishes because the 2 features get identified. Okay. But then, like the way things are glued together and how they vanish, somehow enforces that this corresponding object here is in the composable. Point being, you take any sequence of vector space and linear maps, and you can sit down, you can glue together CW complexes, and you'll be able to represent it in homology. Okay, so it all comes from topology. If it comes from data, I don't know. I don't know how to prove that. I mean, I don't know how to say anything about the expected in the composables for a data set. This I don't know how to say anything about. Maybe it could be in practice that the decomposables you see are not so bad. Okay, so Jay and Sin have recently provided an algorithm that does take a bifiltration as input under one condition I'm not going to mention, and the output is a decomposition into decomposables in a way that mimics the persistence algorithm, but in the multiparameter case. So the running time here is then this big O of n, where n is the number of simplices, to the power d minus 1 times 2 omega plus 1, where d is the number of parameters. So you're doing like, typically in our field, d will be equal to 2 because we're doing by persistence. And w here, or omega, I suppose, is the exponent for matrix multiplication. Now, this bound is not great, but even if it was great, there's a question at the bottom of this slide I would like to have answered. Is like, how do you use this in the composables for anything, right? So let's say that you work at a data analysis company, and then out comes this one to the right here. What do you do? Like, I don't know. I mean, if you can tell me how I can interpret this in terms of my data, we can make money. But right now, I don't know how to do it. So that was, yeah, maybe a little bit negative. So let me mention something that's a little bit more positive. And this would also intertwine with or connect well with what Grigori will talk about on Friday. Was supposed to talk about in 2 hours, where multi-parameter persistence actually performs as in the 1D case. Now it's a little bit constructed perhaps because we really have only one function for R again, but we can construct a 2-parameter module that decomposes just as you would hope. So what have I done here? Well, I've taken a space and have a function, just the height function. And now, instead of taking the sub-level set filtrations, because when we do the sub-level set filtration, a lot of information will be lost. For instance, I will not be, so if I just filter this space from the bottom to the top, well, I will see that there are 2 components of us sticking out here, but I will completely lose, at least in H0, I will lose the information that there's a hole in the middle. Whereas if I would consider the fiber here instead, just tracking the homology of the fibers, I would see that the fibers would then be connected, and split up, and then come back to being connected. And also, if I had something persistent homology, that's something that, like if I took this one and turn it upside down, these 2 branches here would be in this persistent homology. So persistent homology. So therefore, many have sort of level set persistent homology. And there are different ways of defining this, but the one that I prefer is that you look at this as a two-parameter module. So you take an input AB that we're going to think of as a closed interval AB, and we take the preimage of that closed interval and the apply homology. Okay. And now I can identify the full set of closed intervals with that part of the plane that's above the diagonal to the left, as long as we flip the coordinate axis in this direction. So now I take as input, let's say my point A2, A6. I take the preimage. Maybe I should take something a bit more reasonable. Okay, let's just start with A2, A6. Okay, so where is A2, A6? That will be the preimage from here up to here. So we should see in homology in dimension 0, we see one global, like one connected component, and we see H1, we should also see one from the middle here. And now we just go over to the decomposition, because if you run apply homology and you decompose, you will see that this module is completely determined by a bunch of intervals in this upper half plane, or this part of the plane. So if I go to A2, A6, and I'll figure out how many of these intervals contain the point A2, A6, that should give me the dimension of the homology in that, well, for that particular homology dimension. So I would like to know H1 dimension. I just go A2, A6. The point here is that H1 should be equal to 1. And if I take H2, H6, A2, A6, I go here. That's also one block up here. So I see that there's a homology dimension 1. Also in H0. Now you can do that, and you will look at the regions, and you can interpret the different types of regions and the type of the feature, etc. It's like a really rich structure for levels of persistence. And I could spend another hour talking about this, but luckily Grigory will do this for you on Friday, so I will leave it to him. Okay, it's not a little teaser. That is not always bad. Okay, so let me say a couple of words about the interleaving distance. So the interleaving distance is a metric on, well, I suppose classically 1D persistence modules. And for the ones that are indexed over the integers, it's defined in the following way. It's like a weakening of the notional isomorphism. So notional isomorphism would just be that you have a map from n-1 to n-1 and from n-1 to n-1. So that's in both directions, such that they compose the identity in both directions. So if you go up and down, that should be the identity, and down up should be the identity everywhere. But now with the one interleaving, we're not going to take it as an isomorphism, but we're going to ask for the map from n-1 to n0 to m1, such that going from n-1 to n0 to m1 should commute with the internal map in M. So that should, so basically just put in arrows like this, diagonally slanted, shifted to 1 by 1 to the right, and then every possible thing, every diagram there should commute. And the idea being that if I have a feature that lives, let's say, from M0 to M2, then that feature will be detected with M1 and vice versa. Okay, so features like that. And then you have the notion of two interleaving, and then ultimately you just, for let's say the continuous case or in the integer case, the indexing category, just define the interleaving distance to be the infimum over all epsilon, such as M and N are epsilon interleaved. Okay. And now here's a very big theorem in our field, in the 1D case, and that says that the interleaving distance is actually equal to the bottleneck distance. So I can compute the interleaving distance by just decomposing my two persistence modules and computing the bottleneck distance. I get the interleaving distance. And that has many important implications, especially when it comes to stability theorems. All right. Now you go to the multiparameter landscape and you do the same. Right. What do we do? Well, instead of having my morphism now going shifted 1 to the right, it's going to be like 1 along the diagonal. Instead, so I'm going to have a map from M0, or in this case, M prime 0, 0 to M11. There's going to be a map from M11 to M22 prime. Okay. And what's the condition? Well, the condition should be that if I go here, then that should commute with going up and down. So you just add 1 along the diagonal, like 1 shift everywhere from M to M prime and from M prime to M, and then every possible diagram should commute. Okay. And then I can, and assuming you will now deduce what the two interleaving and even an epsilon interleaving should be for R and the index modules. And then we define interleaving distance to just be the smallest epsilon again, such that M and M prime are epsilon interleaved. Okay. So the reason we consider the interleaving distance is because it has great theoretical properties in 1D and in higher D. So let me just mention one thing that's great about the interleaving distance. And in order to say that, we need to talk about what it means to be stable. So I mentioned this sublevels of filtration before. So now you can also do that to Rn. So you just consider all the points that have a function value smaller than some point in Rn. So you get the multifiltration of your space. And then we say that the distance on these multiparameter persistence modules is stable if the distance between these two homology modules, where they come from the sublevel filtration of two different functions, is bounded by the infinity norm between the two functions. Okay, so that's what you say, define a distance to be stable. And the first thing you prove is that the interleaving distance is stable. And that's kind of trivial, it's just from the reality. But then here's something that's highly non-trivial. And then if you assume that the field is prime, so that means that it's a rational zone, like Z mod P, then it's the most discriminative distance on multiparameter persistence modules. If you pick any other distance that satisfies this condition of stability, then it's going to be smaller or equal to interleaving distance, which is a pretty nice statement. So then, with that in mind, you would like to compute the interleaving distance, but unfortunately, it's not possible because even approximating the interleaving distance within a factor of 3 is MP hard. Okay, so that's like, I'm just telling you that you can go from 1D to 2D, but everything becomes hard. Okay, but luckily, in the second part of the talk, I will tell you about some recent developments that allows for a bit more optimism. Okay. But here's one thing though that's quite nice. This is by Blumberg and Lesnick, fairly recent work. So I mentioned the Hausdorff stability for the bottleneck distance persistence homology. So here they have a measured theoretic analog of that statement. I don't want to define the Prokhorov distance. You can look in the survey. I just want to draw a picture here. So here's one other bifiltration that I didn't mention, and I think the easiest way to define it is just simply by looking at this picture. So you take a bunch of points in, let's say, the plane, and now I take another point in the plane, and at the radius r, I consider only those points that are covered by at least m disks. Okay, so if you just then do the normal check thing where you increase the radius, then that will be the multi-cover bifiltration where that m is equal to 1, because you're only saying that the point should be covered once. But let's say that I'm only going to consider the points that are covered twice or thrice or whatever, then you end up with this bifiltration. And that's actually been studied, I think, Ellsberg and Osang were perhaps the first to consider this. I'm not entirely sure. But that should again be a somehow proxy for outliers, because the points in the important regions, those with the high density regions, would then be covered by many disks. Okay? So if you consider this bifiltration, this they're called multi-cover bifiltration, and then you compute the interleaving distance between the corresponding homology modules that will be bounded by the Prokhorov distance. So that's a measured theoretic analog of the Hausdorff distance you can look at. But I don't want to define it. Okay. So I'll say a few more words. Then, all right. So that's a positive result that tells you that interleaving distance or the multiparameter persistence has good theoretical properties. But now let's be a bit more concrete and look at different invariants. So we go from data to multifiltrations to apply homology, and then in the end we like to compute some invariants. So the simplest possible invariant you can compute is the Hilbert function. Okay, so what's the Hilbert function? You just look at your module and you record the dimension everywhere. Okay, the dimension. The one that I will spend most time discussing today is the rank invariant. You just record the rank between any 2 points. And then for the more those who like commutative algebra a little bit more, you can also consider the multi-graded Betty numbers, where they are actually taking a free resolution, minimal free resolution of your module M, and then it will be the number of generators at each step here. Of course, I don't have time to define all the terms I'm introducing right now, but what you should think about this as these 0 being the number of generators, so stuff is born, and then B1 will be the number of places you have relations where things are, you have features that are born at, let's say, incomparable points, and then they come together, and then they merge, and then somehow you need to encode that in your modules to have a relation. Okay. And then another thing that we do consider quite a bit, that also Claudia mentioned, is the fiber barcode. Because if I take now a 2D module, then I can always take the restriction to a line, and since that is going to be a totally ordered set, I know that it has a well-defined barcode. So what I can do is just consider all the affine lines in non-negative slope. I take the restrictions, and I look at the barcode as a various line around. Okay, that's a fiber barcode. And all right, okay, so now I'm going to show you some plots. But what I wanted to mention first here is that if you do persistent multi-parameter persistence, then it's very easy to come up with some bifiltration. But then ultimately the object you want to study, you want to store in the computer in a minimal possible way. So what you do is that you take your bifiltration and you compute a minimal freeless or a minimal presentation, because it's the sparsest way of storing your homology module on the computer. And this is something that the Rivet software I will discuss momentarily does very efficiently. And another thing that Rivet does very efficiently is to compute a backbone that allows you to look up the barcode of any line in constant time. Constant-ish. What is it? Is it this? Do you remember?
There's a lookup. The speed of the arithmetic.
Yeah, okay.
Plus the size of the
but yeah. So what does Rivet look like for the bifiltration we looked at before? Well, here we see that there's an H1 that's born here, and that's reflected in multiple ways. But for instance, we see that there's a gray area here, and gray means in this case that the homology dimension is equal to 1. So I have the bifiltration, I compute this output with rivets, and whereas gray means that the homology dimension is 1, whereas green, that means that there's a bed is 0, that means that something is introduced, a new feature, whereas red is where something dies or where something is identified. So for instance, you have a feature down here that it's a bit hard to read from this plot, but I believe it should be let's see. Yes. So the point here is that we have a feature in the middle here. So there's a H1 in the middle to the left here, and then it also appears here. So that feature in the middle here appears at 2 incomparable scales. So that introduces a Betty 0 here and a Betty 0 here, but then you have a Betty 1 telling you that they are now actually merging, so we shouldn't double count that feature. So what Rivet does is basically takes input bifiltration, outputs where it's gray, where the type of shading of gray will give you the dimension of the vector space over that index, and then you can like live, you just slide your line around, and you can just look up all the possible barcodes when you move your line. I would normally show that, but I don't have a computer here, so you can just download and use this software itself. It's very easy to use. Okay, so if you go back to this other example, I also mentioned with the circle and the dots in the middle, then if I take now the barcode of this one, and down here in this direction will be density. So I'm going to start with the most dense points to the left. I'm going to add less and less and less dense points. So if I restrict to this line, this vertical line will just be the normal RIPS persistent homology at this point cloud, because I'm saying I'm going to consider the barcode when I have fixed density of at least 10 and doing normal increasing the radius. So then I get this barcode, whereas if I say density at least 18, as I mentioned before, it's going to be very unstable in the choice of this density parameter. You will get this barcode here. And then you take your line and just slide it around, and you see that you have this one bar that somehow is robust to your different choices of angles, left and right. Okay. So you mentioned one more thing. So here is a plot. They studied, I think, in Rabadon's lab, Colombia. They studied HIV, and they used Rivet. Not entirely sure what conclusion they made in the end here, but I think the point of the plot is to show that already the Hilbert function is able to indicate that there are at least, I think, 5 major clusters in this HID data set, because if you look at the dimension vector, and then you can use your F1 line to kind of slide it across, and then you will see that there's actually the same feature persisting, because of course, theoretically, just having the dimension vector doesn't tell you that there's a feature that persists, because theoretically, you can just put dimension vector, you can have dimension 1 everywhere, and everything is a 0 map. But that's a bit unlikely, but you can rule that, you can't rule that out. All right, so I think I'll take a break now, because halfway. So are there any questions? Good.
So I wonder the calculation of the multi-dimensional distance you mentioned by the
Yeah.
So of course I understand why it's totally flat and everything, but what sort of output does it gives this the rows of representations, sums of representations?
So the output is yeah, well, so of course the output would be equivalent to something like this to the right here. So yeah, the vector space and linear maps. But I assume I have never, so I read the paper, but I never actually played with the code. But I would imagine that you could also do this such that the output would be for the in the composable, you have the set of generators and the relations. So you have a minimal presentation for the in the composable.
I think it decomposes the presentation.
Yeah.
And did I understand correctly? At some point you said that I mean for some it was there for some filtrations or multi-dimensional filtrations coming from topology, some sort of nice data complexity is much simpler somewhere.
No, this I cannot claim that.
Yes, yes.
I can hope that.
Yeah. So we have no evidence of what would happen. Some constructions of these complexities, because the maps are the maps, and not all presentations, they won't give you all the presentations.
Yes. Okay, so I can give you one special case that things work exactly as you would hope, and that's in this setting here. Then you know that it's going to be precisely the one decay to decompose into this intervals, etc., etc. But once you go to more, I mean, I don't know. I played around with some simple examples, trying to compute, and you know, it's you don't see this full wildness, but it's also not too unlikely that you will find at least one indecomposable that's not just an interval, it's something a bit more involved. So you need to deal with them at some point.
Last little question, sorry. So I was very interested in your this example where you had A, B, or interval A, B, bidimensional persistence. Look at the intervals within the level sets.
Ah, yeah.
Okay? And because it relates to some of the things we're considering as well in direct approaching, we always have fixed endpoints, so we always have at least beginning and end. So the space, it's a space of paths, which is more complicated. Have a space depending on 2 parameters, like interval-based things. And I didn't know about what you mentioned there, and are there any references which would explain the relation between what you see with these interval-based tables?
Well, there's a recent introduction to multiparameter persistence I could highly recommend. No. I mean, many authors have written about this topic. Gregory will look at this from the sheaf theoretic point of view. But I think in general, levels of persistence is underappreciated. I think it serves a more prominent role in the literature because it's a finer invariant. And actually, well, I have many other pictures showing So basically, if you look here, you see that there's H0 here, like an open triangle here, and that corresponds to the fact that the fiber somehow breaks up at A4, and then splits into two components and come back together. So you can see that goes somehow from A4 to A5 there. But then what happens to H1? Well, if an H0 splits up, that means that there has to be an H1 forming, and that's reflected in this one. And what you can do now, I guess it's quite beautiful, you can construct what's called a multifiltration strip to take this from all dimensions. It's actually, okay, this is not what Grigory will tell you is that you can take now, you can connect the levels of persistence across different dimensions because they're really connected by that connecting map in the multifiltration sequence. You can also extend with relative homology, and then you will get this big strip where you can see how like all these features in different dimensions are just restrictions to one bigger feature to the given concept. Pretty nice theory.
So does your introduction here, or does, you know, if anyone has considered multi-parameter zigzag or multi-dimensional zigzag?
Yeah, we mentioned there's at least mention of one such bifiltration that comes up when the study of a time varying data, I believe. So because if you study like flocking or like behavior, like things like you do clustering, but then your points, so let's say you fix your scale R and then you have some points clustered together, but then they break up. And then they come together, and you can somehow form a zigzag tracted evolution. But now you fix your scale R, and you allow the T to vary, but you would like to let the R vary small.
So do we have these same results? Like there's a unique decomposition in decomposables that zigzag that holds?
You can take any small category.
Okay.
Yeah, generally speaking, part of the literature on multiparameter persistence is very concerned about general concept representations. This part would apply. Are there more questions?
So you mentioned that, so you have this multi-parameter persistence, and then you can put these lines and you get a barcode, right?
Yeah.
So would it make, if there's some way of taking the lines, the barcodes that you get from the lines, and if you have some family of these barcodes, can you recover some information about what the two-dimensional picture looks like?
Yes. So what I'm going to discuss after break is what's called the rank invariant, which is this one, which records the rank of every pair of points, and the collection of all such lines is equivalent to this information. It's equivalent to knowing the rank between every pair of points. And from this, you can do fun stuff, and I will show you.
Okay, awesome. Thanks.
Sorry again. So yes, you just answered one of my questions about set persistence and whether that would apply also to more general set persistence. But there's one thing in set persistence that I don't understand. I haven't tried enough. It's distance. Because I mean, in that case, you can obtain the diagonal and everything. But in the set persistence case,
Yeah.
what do you do?
Yes.
Are they well accepted notions in general persistence?
There are several papers, different approaches. I have one paper myself. I have a certain bias. But I can tell you what we did in the zigzag case. So in the zigzag case, we realized, I don't know, I forget where I was here. Oh, I should go back. So in the zigzag case, what we realized, at least if it alternates all the time, we put the zigzag on the diagonal in the extension. So we took that one and we used co-limits to extend that module to the whole indexing category, and then we interleave the bigger up, because basically you find a larger object, a larger category where you can interleave, and you embed them there, and then you interleave. And you have a fully faithful embedding, which is nice.
Any more questions? So let's thank Magnus again. And well deserved break. So when are we back for the second part? 10:30?
No, we didn't.
Okay. All right, so we're back with Magnus, part 2, which will be more focused on one of the invariants that he was talking about in the first session. And this will be the ranking invariant.
Thank you. All right, so the first part, we focus on what doesn't work. In the second part, I will focus on some recent advances that are quite optimistic, I would say. So the rank invariant is a very simple invariant. You take 2 points in whatever pole set you have at your hand and at your disposal, and you compute the rank between those 2 points. And the collection of all those ranks, that's the rank invariant. Of course, we will be focusing on the grids today for the most part. And okay. So I think the computer has frozen. But
The focus is
okay. All right. So in the 1D case, considering the rank invariant comes at no expense, because if I have the rank invariant, I already showed you that you can compute the barcode because it was just a inclusion-exclusion formula. So clearly the rank invariant determines the barcode, and trivially the barcode determines the rank invariant because somehow the rank is additive with respect to the direct sum. If you have the bars, you can easily deduce the rank. Now, here's one thing you can do with the rank invariant, also what Claudia mentioned, is that you can compute distances. So the matching distance is only sensitive to the rank invariant, but we can actually compute it and approximate it in practice. That's already good. So what is this? Well, remember this fiber barcode. So we take now the restrictional lines of actually positive slope, FM lines of positive slope. And we're going to assume that the lines are parameterized such that it's of the form dt plus b, where the minimal component of this is a vector in Rn, and its minimal entry is equal to 1. Okay? This is an equivalent way of defining the matching distance. It's just because now I'm going to take restriction to a line, and abstractly it gives me some bars, but now I'm going to compute distances. It actually depends on the parameterization. So I need to choose a nice parameterization. And what this means is simply in a 2D case that if it has a slope of greater than 45 degrees, then we can think about each bar as just being a projection down onto the horizontal line, such that if it's near vertical, then you have to be very, very, very persistent in order to have a long burst, definitely. Okay. So now you take all your lines, you take the restrictions of M and N to those lines, you compute the barcodes, you take the bottleneck distance, and take the supremum of that over all possible lines. That's the matching distance. And it's quite interesting that you can compute this exactly in n to the power of 6 log n, where n is the number of generators in relation to the m. Okay, so it's not very fast. But what's more important is that it can be naively actually very efficiently approximated. So you can use this in practice, and there are implementations out there. But again, it's only sensitive to the rank invariant. But I think what I'm trying to argue in the second half of the talk, although I'm not entirely sure if I agree with myself, is that we should just dispense with all that algebraic technicalities and focus on the rank invariants. Maybe, I'm not sure. I'm getting there. Okay. So what's not great about the rank invariant is that it's not a complete invariant anymore. So for instance, if you consider these two bifiltrations here, so I simply have two triangles glued together, but in the one case, I fill in the top one and then the bottom one when I go top and to the right, and then I fill in both, Whereas in the other case, I fill in the top one in both cases, and then I fill in the bottom, bottom one. Now, if you take this one in H1 and you compute the rank between any two pair of indices, you see that the ranks are equal between the two cases. If the rank of P here is 0, the rank of P here is 1, the rank of P here is 1, etc. So the rank invariant does not distinguish between these two bifiltrations. However, the algebra does, the zigzag persistence does. And so if you decompose these two diagrams, you'll see that the one to the left will decompose into something that's KK and 0, which actually reflects the fact there's a feature that dies here, but does not die here. And then the other feature dies here, but not here. So that's reflected in the algebra. Whereas here, in the right-hand side, you'll see that there's one feature that persists along the whole hook, and the other one only one vertex. So the algebra is more discriminative, and the rank invariant fails to see this. So already for very simple filtrations, the rank invariant is not a complete invariant, but it has other nice properties. And it is still a very useful invariant. So let me mention two recent applications. So it's not like multidimensional persistence only has potential. Its potential has also been utilized. Its potential has been utilized in two recent papers, and well, more papers, but these are fairly similar, and those are the two we survey in our introduction. So the one to the left here is a paper out of Oxford from October last year, where they studied, well, you have tumor cells, and then you have what are they called? Like the immune cells are somehow distributed on the boundary of the tumor, and then you would like to study how the immune cells enter the tumor. Okay, and they use this for using persistent homology. Okay, I will not go into all the technical details. You have carefully explained this in the introduction. Of course, you can also look up the paper itself. The point being that when they did this with this optimal data, so actually this is what I'm showing here is synthetic data, but they also do this for neck and head tumors, I think, with real data. But I only have this picture for a synthetic case. So if you do this in the perfect data, the idea, okay, so the idea is that you have the cells, the tumor, the immune cells are distributed on the boundary. So then you have an H1, but then as they go towards the center of the tumor to kill off the tumor, H1 dies. And then depending on the chemotaxis parameter, you can plot an H1 curve that at scale R gives you the longest bar in the barcode. This is their setup. Point being, in the case that you have perfect data, everything works well, but then in practice you have measurement errors, so you don't only have the data divided like nicely like on the boundary, you also have outliers floating around, and if you try to do that with the normal 1D persistence, it breaks down, you're not able to do the analysis you would like to do. However, they use the multiparameter landscapes as introduced by Oliver Weipens, who's also co-author here, which is a generalization of the landscapes from 1D persistence. And considering the multiparameter landscapes, and with the corresponding norm of those landscapes, they again can construct certain curves, and those curves are used to give the desired results. Okay, sorry, this will be technical if I'm going to go into details here. So if it sounds interesting, just look in the survey or in the paper. It's also very accessible, their paper. The other one is similar data. So they had immune cells and cancer cells. And now the question is, you have some tissue, and for that tissue, take two pictures. One gives you the density of cancer cells in a pixel, and the other one gives you the density of immune cells in each pixel. And the question is, given only these two pictures from that tissue, can you say something about the predict how long you're going to survive, essentially, if you will survive the cancer? And so Mathieu Carrière and the Blumberg, they study this data. Now it gives you a natural bifiltration, because for each picture now you have two function values. You have the density of cancer cells and you have the density of immune cells. Now you get the two parameter bifiltration. And they ran that analysis, and they were actually outperforming the state of the art within the field where they actually studied these images. And they compared to also doing different slices like 1D restrictions, but it was much better to just consider the full 2D picture and using what they call the multiparameter persistence images, which is a generalization of the persistence images from 1D persistence. Okay, so the rank invariant perhaps not as discriminative as you would like it to be, but it's still computable and it has nice applications now. So that's encouraging. Okay, so given that the rank invariant is so nice, maybe we could construct a barcode for the rank invariant. Okay, so I'm going to define a good barcode to be a subset of my pole set, or in this case, a subset of the grid, such that if I would like to compute the rank between any 2 points, that's just going to be the number of subsets containing those 2 points. That would be analogous to the 1D case where like the rank is just a number of intervals containing A and B, okay? So for instance, in this case, I do have a good barcode because this thing to the left here, the rank here, is, you can check that this rank invariant of this guy is equal to the sum of the rank invariants of these two guys. And the rank invariant of this one is completely determined by this int, like this, I don't know, subset here, and this rank invariant here is completely determined by that subset there. Okay, so if I like to compute the rank invariant, I just look at the intervals and I can easily read off the rank invariant. But then you look at this example, and then you ask yourself the question, can I find a good barcode for this one? And then you stare at it for a little bit, and then you realize you can't do it. Because what happens is that the rank, for instance, from the left to the right here is going to be 1. So there has to be whatever interval would be here would have to contain this chunk in the middle. But that chunk in the middle would have to be connected with something that comes from the bottom here, because the rank from here to here is 1, and from here to here is 1. So whatever ends here would also have to be connected down here. So if you run this analysis, you would see that your interval actually has to contain this whole part here. And then you go up here, here's a symmetric argument, and then you see that it also has to contain the upper left square. But that's impossible because you can't have an interval here that is supported on like this part of the square, except for the bottom left and top right corner, because the composition of the maps from the middle on the bottom to the middle of the top is equal to 0, and the rank there is 0. So if you run the analysis for this example, you will see that, well, there's no good barcode. Okay, right. We're not going to give up that easy. So now I'm going to advertise a different paper, which is written with Steve and Stefan Offman, where we work with sign barcodes. We say, okay, we're going to be a bit flexible. We're not going to just take the barcode. We're going to allow the barcode to have positive and negative multiplicities. Okay, I'll show you what this means. So just to introduce some notation, when I say an interval, I will mean something that's convex and connected, and then not convex in the standard sense, but convex in the sense that if I take 2 comparable points, then all points between them will also be connected, contained inside the interval, and it's going to be connected. So every 2 points inside the interval can be connected by a finite shape of comparable elements. And a rectangle is just something that has a unique minimum and a unique maximum, and a hook is what you get by, it's a hook. It's something like this. So somehow it comes from all the way down to the bottom here, like to infinity here, and then it just cut out this part here. That's going to be a hook. And then of course they're symmetric. So it's like a free module. If you like something that generated a point projected, but then you remove a projected like a larger index. You take some quadrant and then you remove a larger quadrant. I guess it's better to say. And then these also have the corresponding concept modules or equal modules, or just the case everywhere by identity maps, like we saw in the one case. Okay. So you have subset of your pole set that's an interval, then you put the case everywhere in the interval, like connect all those cases identimorphisms we have a persistent modules. Okay, so we saw that this one could not be represented with a good barcode. However, it is equal to the rank of this interval module here minus the rank of that interval there. Okay, so I have taken my rank. Of course, it's a bit hard to verify this now, but you can verify that the rank of this one, the rank invariant, is equal to the difference of these 2 rank invariants. Okay. All right, it's promising. But then you realize that it's also equal to the rank invariant of this difference. So I have 2 ways of expressing the rank invariant by using different intervals. Perhaps you would like something that's unique, and what's nice is that we can get uniqueness. And I will tell you how. So assigned rank decomposition will be a pair of multisets of rectangles. I'm going to focus on the rectangles because then I will have uniqueness. Pair of rectangles such that the rank invariant is equal to the rank invariant of one collection of rectangles minus the rank invariant of the other collection. Okay, that will be a assigned rank decomposition. So now the question is, for any 2D module, can I always express the rank invariant as a rank invariant of some rectangles minus the rank of non-other rectangles? Okay. And yeah, here's a little intermezzo because it somehow fits nice with the story. So what Steve and Vadim, myself proved, I forget what year, 2 years ago maybe, we proved that if you consider the rank invariant on 2D modules, then the rank invariant is actually a complete invariant on the rectangle decomposable modules. So if you know that you have 2 modules that decompose into these rectangles, and they have the same rank invariant, then you know that they have to be isomorphic. And they have the same. Okay, so we prove that. It will be somewhat related to what I'm going to say next, but this is just a nice observation. Okay, so what we also observed in that paper is, given that you know that your persistence module is rectangle decomposable, how can I find the rectangles in the decomposition? Well, it turns out you can use an inclusion-exclusion formula that generalizes the one you know from 1D persistence. Okay, so remember we had like something that you take from the rank from S to T minus the rank from S to T plus 1, etc., etc. You combine the pluses and minuses, and you did that. You got the multiplicity of the interval. You do the exact same thing here for the interval, let's say, from S to T, then the multiplicity of this interval in decomposition is given by this inclusion-exclusion formula. No, but you need to consider a few more points because you're thinking, for instance, okay, I have something that lives at S and lives at T, but then it dies when I go 1 up, and it goes 1 when I go to the right, but now I kill it off twice, so I need to add it 1 more time. So I mean, use the inclusion-exclusion formula. So the point is that this one is a strict generalization of the one in for 1D, and it gives you precisely the rectangles in the decomposition. Okay, that was a nice intermezzo. And now we say that the rank decomposition is minimal if R and S have no common rectangles, because obviously we're not going to have uniqueness if you allow R and S to have the same rectangle, because then they will just cancel each other. If you take any rank decomposition, RS will add the same rectangle to R add to S. Well, the rank of R minus the rank of S will then do the same as before. If I take here, add any rectangle to this chunk here and add the same rectangle to this one, it's still going to be a rectangle like into rank decomposition of that one. Right? Yes? Okay. So we're going to assume that the intersection between the two is the empty set, because only then we can get uniqueness. This I'm going to skip. And here is our theorem, which says that if you have a multiparameter persistence module over a finite grid, then M admits a unique minimal rank decomposition. So I need to give credit where credit's due here, because we're not the first ones to go down this direction. So Kim and Mamoli, they get similar results for a different definition of the rank invariant. More like a generalized rank invariant. Amit Patel was the one who actually started discussion down this line 2 years ago, and also Shiba collaborators consider similar problems where you do not have uniqueness because they decompose the rank invariant using all possible intervals. So then they have existence but not uniqueness, but you can do it in different ways. Okay, but what we do is also we prove vastly more the general statements in our paper. But for position, I didn't want to go into that, but you can have persistence modules over Rn that are finitely presented, or you can have persistence modules over locally finite pole sets in general, whatever locally finite means. And we can also consider this more general rank invariant that I'm also not going to introduce. Let's just focus on the most simple aspect of that. Okay, so what's nice about the rank decomposition is that we can actually visualize it using bars, like in analogy with what we do in the 1D case. Because if you take now this one, for instance, okay, so here's just an interval, staircase interval, take the rank decomposition. Well, then the rank decomposition with rectangles is going to be this one minus this one. This will be the R and this will be the S. Now, if you try to visualize that, it's going to be kind of clunky, especially if you superimpose all these rectangles. So what we realized was that, well, a rectangle is uniquely determined by its initial point and its terminal point. So just take a straight line from its initial vertex to its terminal vertex. That's what gives me a line. So now I go down here and I plot all the lines in R with blue and all the lines in S in red. Now visualize the rank invariant. And now, how should I interpret this? Well, the way I think about it is that I see something that's blue that's coming from down here, and it lives here, and it also lives here. But now there's thrown in something red in the middle there, and that's there to tell me that I'm double counting that feature. Because I need to remove some rank here, otherwise I'm getting too much rank. So I have this feature that's here, 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 and now these reds are here to tell me that I'm double counting, and it somehow trace out the shape that we saw there. And you can do other things as well. So for instance, if you have the rank decomposition and you would like to have the rank, just compute the rank between any 2 points. Well, then you just take, let's say I would like to find the rank from S to T here. So then will then simply be only all the rectangles that contain S and T up here minus the rectangles that contain S and T down here. Then of course you get the rank invariant immediately. And that would be the same as all the lines here that start in the downset of S and end up in the upset of T. So if I would like the rank from S to T, I just take all the lines that go from here and end up here. So that will give me 2 blue minus 1 red, which will give me 1 in total. And then if I would like the fiber barcode, well, I can just take the restriction to any line and the restriction of decomposition to a line will give me also a rank decomposition of the restriction, but it doesn't have to be minimal because it could have some intervals that are repeated, but once you throw out all the repeated elements, you will just get the barcode of that restricted line. And the reason for this is that if you take a 1D persistence module, it's completely determined by its rank invariant. That means that the barcode of the restricted line is given by the rank invariant, and the information you have here is precisely the rank invariant. So when I take that restriction, I'll get that barcode back. But as you see here, I will have 3 intervals in this restriction and 2 intervals here, but 2 of them will have to cancel. Because when you take the restriction, you know that you just have a normal barcode, so there will never be any negative terms. Okay. So here's an example, synthetic data, well, that we considered. So we took something like this. We had 3 holes, A, B, and C. I'm going to filter by height, and I'm going to filter by radius. So then we get the multiparameter of this form. And you see that the feature A here somehow lives in this region here. So it's born here. It's kind of alive here, I believe. I'm just going to see it. And then this is the region it's alive, and feature B is alive. Over here is a little bit funny because feature B is actually born at 2 incomparable points. So one where it just goes in the middle here, but also over here there's a tiny hole here when these 2 come around and form a hole, and a feature C lives up here. So what does the rank invariant computation look like, or the decomposition look like if you run this experiment? So now this is very coarse, of course, it's a discretized grid, but then the output is some lines here that reflect some noise in this column, but also one line that goes diagonally like this, which represents the interval ending up here. So that's the feature A. We also trace out feature C. And feature B is interesting because now I have 2 lines that are born at incomparable points. One is born here, one is born here, but then there's also one in a red one because I'm double counting that feature. So because I have this shape, then I can represent this shape by just having a rectangle. So this one. Okay. So here's another example. bit more involved. So here we had some clusters that are generated, so they appear at different density scales or cold density scales. So I keep adding points of lesser and lesser density. And then we can see at the given scale here, you had 3 different clusters. Another question is, can I find these clusters in my sign barcode? And perhaps it looks a little bit messy because this is actually the output of the computation. But then what you could do is, first thing we notice is that, okay, you do H0, always going to be one global H0 component. So it's always going to be a line from the initial, in this case, it will always be a line from initial vertex to terminal vertex representing the global connected component. So that's just this line here. So down here, I just restricted my attention to all the lines that come out of the initial vertex. And then I dispense with that line, and I look at all the lines that are left, and that will give me this other cluster, D, which is the other cluster that's alive down here. You can see how that cluster traces out this nice shape here, where it's like all the points where it merges with A, and then the red, well, and then the red lines are there to tell you that you're double counting. And then the cluster C, I restricted my attention to all the lines that are generated at the index 0, 1. So now you can somehow deduce, well, I mean, so the target maybe, at least to give you some indication that there are 3 clusters in the data. Okay, so do we have stability? Well, in a weak sense, we do. So if you take the rank decomposition of this one, then that's just going to be the rank of itself because it's a rectangle which goes off to infinity, let's say, to the endpoint of this grid. So its rank decomposition is equal to itself. But then I make a small dent into this one. So I'm almost the same thing. It's just I made a little dent here. But then I can really change the rank decomposition because now if I would like to describe the rank of this one, I will end up with having something that goes up to infinity like this, and something here that goes up to infinity. And then I need to add this one to make sure that I'm not double counting because there's only rank 1 along this diagonal. So the stability tells us that if I take whatever I had to add here in order to avoid double counting, I combine that with what I had in my original module, and then I take the new R in the perturb module and combine with what was in the S prime, the other module, then those two will be close. So specifically, the matching distance between this one together with this one from this one together with this one will be bounded by the interleaving distance by the 2 original modules. Okay. Or the matching distance, maybe it's a better idea. And there's been more progress done in this by Steve and Luis Coppola, trying to well, give finer version of stability. Okay. So how do we compute the rank invariant? So this is an algorithm that was first in Dimitri's and then we rediscovered it from our old paper. And if you have n simplicities in your bifurcation, you can compute the rank invariant in n to the power of 4 using vineyards. So I'm not going to tell you how exactly that works, but I can give you a naive algorithm that Steve has an intern now who has implemented this algorithm. So we hope that we will have accessible code quite soon to compute the rank decompositions, etc. Because first step is to compute the rank invariant, obviously. And so it's quite kind of neat. The idea is simply, if you like to find the rank invariant with any pair of points, it's sufficient. It suffices to take any ij in your grid and then take the path that goes along the axis to the left here, up to height j, and then you go to the right to horizontal towards I, and then you go up, and then you go to the right. If you do this for all I and j, you compute the rank invariant between any pair of points. Okay, so how is that? Well, in this case, I wanted to find the rank between this point and this point. How can I find the rank between this and this point? Well, if I take now I compute the barcode along this restriction, that's just going to be all the intervals that contain this point and this point in this restriction. So if I do this now for all such I and j, I will actually be able to deduce the rank invariant between any 2 comparable points. So how many such paths are there? Well, there are n squared because there are n choices for I and n choices for j. And how long does it take to compute persistence? Well, that's n to the power of omega with that matrix multiplication constant. So in practice, O n to the power of 5. But you can improve on this using Vineyards, which is a technique that allows you. So if you have a filtered simplicial complex, and then you have a barcode, and then you swap the order of two simplices, and then you say, what's the barcode of this swapped thing? Then I don't have to recompute everything. I can in linear time compute the barcode. Vineyard computation. So we could actually use the same here, and then we could take the barcode along one path, and then we could take the path that just goes next to it, and we can update the barcode from one path to another one in linear time. And that takes us from n to the power of 5 to n to the power of 4. Okay, and now we have this algorithm for computing the signed barcode decomposition. And the reason I included this thing with the decomposition before, because I found it a little bit funny, we had this very involved algorithm for computing the rank decomposition at some point when we were studying this. And then Steve, I think, just sat down and said, what happens if I take our inclusion-exclusion formula and I just run it on the examples? What happens? And then it turned out that the output was precisely the rank decomposition. So that the formula we had for computing the rank decomposition when you had a rectangle decomposable module, if you just applied it to any multiparameter persistence module, it actually gives you the signed barcode decomposition, which was, okay, well, why is this? Why is this possible? Well, the proof of correctness, or the reason for this, lies with what's called the Möbius inversion. So you can prove that you can obtain the multiplicity of the interval ST by taking the rank invariant convolving with the Möbius function. So I cannot go into the details here, but if you do that and look at what that looks like, then you will see that the multiplicity of ST will be precisely this formula here. Okay, so we found it, and then we also discovered that someone else had been looking at something similar. But yeah. Okay. All right. So now I'm going to just wrap up in 5 minutes, but I wanted to end with a deeper explanation for what we've been doing. So we saw here that we have the rank invariant. You can express it uniquely in a rank decomposition using rectangles. We can also get a unique decomposition using hooks. Okay. And let me see if I can tell you why that is the case and why that's interesting. So there's in homological algebra, there's this idea of, or it's not really in homological algebra, but you would like to do homological algebra, but you don't have kernels and co-kernels. Okay. So then there's this notion of exact category. If you're interested in this, you should look up the survey by Theo Buhler on exact categories. It's basically you take certain short exact, well, they don't have to be short exact sequences, but okay, so short exact sequences, and you adult them with some structure, and then you call those to be the what they call like the co-kernel pairs or something. I like the pairs you care about. That is a way to take a category and do homological algebra without actually talking about kernels and cones. So what we did is that we considered our persistence modules, and then we defined a short exact sequence to be rank exact. If, of course, it's going to be short exact, but the rank invariant of the middle guy is equal to the sum of the rank invariant of the M1 and M3. So the rank invariant of M2 is equal to the rank invariant of M1 plus the rank invariant of M3. You look at the definitions and you run through the machinery, and then you prove that the collection of rank exact sequences defines the structure of an exact category on the category of D parameter persistence modules. Okay. So this you check. There's something to check here. It's not trivial, but you can prove this. And what's nice is that then you can also reference earlier work in the literature. It gives us immediately that our exact category has enough projectives. Okay. So in particular, we have that our category has finite projective dimensions. So we have projective resolutions with respect to this exact structure. Okay. And as direct, and the projectives are especially these. There are these hooks. Okay. Now I have that. I have the projectives are the hooks. I have finite projective dimension. So I have this exact sequence, exact with respect to the right exact structure, with or like a projective resolution. And as a direct consequence of this is that the rank invariant of M is equal to the alternating rank invariance of the PIs. It just follows from how we define an exact structure and what a projective resolution means. Okay, so this actually gives us already an existent result that I can always take a 2D module and express it as the rank invariant of hooks. So it's just given here. So this is a very different approach from what we did before. And then what you can do is you can take this rank exact structure as exact category in general, and you can talk about the growth in the group. Okay? So what we do in this case is that we take our d-parameter persistence modules and we quotient that that free abelian group on the isomorphism classes of d-parameter persistence modules with respect to the relation that M2 is equal to M1 plus M3 if they're connected by rank exact sequence. Then you get the growth in the group K0. Okay. And by construction here, we have that the rank invariant defines a linear map from the growth in the group to all the functions so z to the power of st is just the number of rectangles in my pole set copies of z. Okay, so st is just a rectangle, and then just take that number of copies of z. Okay. So in other words, it's just a function that so you have some function here, you assign some integer to any rectangle. Okay, so in other words, I get a linear map from the growth in the group to z to the power of the number of rectangles in my pole set, and by very much by construction, this is going to be a linear map because how we are defined that M2 should be equal to M1 plus M3. So it respects this linear structure. And then my final slide is that we prove that this map here is an isomorphism of abelian groups. So in particular, we have that a basis for K0 on the growth in the group is given by either the hooks in the projective resolution that will give you a basis, or you can use the rectangles to also give you a basis. And the moral here is that two multiparameter persistence modules cannot coincidentally have the same rank invariant. There's a deeper explanation. If they have the same rank invariant, they're also going to be equal in the growth in the group. So they are somehow connected by these short set sequences, their own set sequences. That's what I was.
All right, thank you. Questions? Yes. Great.
Yeah, it's me again, sorry. Yeah, I have a stupid remark. It struck me from the beginning of the talk about invariants and this decomposition, that somehow, I mean, if you consider all generators who operate the grid of multi-dimensional persistence, it seems to me that in multi-dimensional persistence, you have some sort of action of some symmetric group of generators. And in your example, you have wanted to distinguish between the equation of one in triangle. And so if you sort of move around the generators to the symmetric group, you won't see the same action. So somehow on the moving itself.
Sorry, you mean this example?
Yeah, this one. So somehow it seems that you want to know not only the birth and death of the generator, but also sort of how coherently they act onto the grid. So if you look at symmetries, then something which sounds like some action on top of this. And it struck me also the shapes. It's like the patterns on the set of generators.
Yeah. So you mean to identify which ones are the same? Or?
Yes, because when you want to exchange through symmetric groups some of the generators, of course, to be coherent, you have to act coherently through the rest of the grid. So you don't reach all representations, you reach some specific kinds of representations, which in theory you can classify them. So it's part of the
think in like similar spirit, there's this generalized rank invariant where you try to achieve something on what you're saying now. So for instance, you don't only consider rank between any 2 points anymore, but you consider the rank across any subdiagram. And what? So you take any subdiagram.
Yes.
So for instance, in this case, what would be the rank? Then I can take, for instance, the rank across this subdiagram here. Let's say this part here. And then what you can do is that you compute the limits and the co-limits over that subdiagram. So in this case, you will see that the co-limit is actually equal to 0, whereas in this case, the co-limit will be equal to k. So that's more generalized rank invariant, where you consider the limits and the co-limits over all subdiagrams. We actually capture that there's a feature living here, but there's not a feature living here.
Yeah, I think we have also some ideas.
Questions? Yes, brother.
Thank you, Michael. Can you tell me more about the inequality that given the matching distance, so the matching distance for the sign of the barcode and the matching distance for the ranking variance? So, counterintuitive to me that the one for the sign barcode is smaller than the matching distance.
Yeah. So it's actually, okay, so what we would like to understand better is the following. So you compute so the matching distance is completely determined by the rank invariant. And what we have here is the rank decomposition. It's also precisely the variant as equivalent information. So could I not compute the matching distance from using these geometrical shapes only? So is there like a combinatorial matching distance in that sense, using these blocks? Because right now, what we define the integrated distance is indeed going to be very often, I think, smaller than the matching distance. It's not going to be equal to it. So we would like to have a distance on these ranges that coincides with the matching distance.
I was thinking this example, but maybe this is not. Let's assume that M is L-shaped module and prime is trivial. So the matching distance is finite because what is the decomposition of an L-shaped persistence module? It's R is a free module and S is another free module. Is that correct or is it wrong?
No, it will be a little bit different, I think, because so it's not just a difference between these two.
Oh, it's not. Okay.
No,
that's why
because then the rank from this point to this point will be too large because you not subtract, because if you have the L shape, then the rank from here to here should be 0. Whereas if you just take these two, this one minus this one, then the rank from here to here would always be 1.
Okay, so that's why, because I'm not taking the correct decomposition. So, is it
So can I try an explanation for the fact that you have an inequality in this direction? So suppose you want to compute in the one parameter case, you want to compute the matching distance between 2 barcodes. Okay? Now suppose that you are allowed to add the same bar to the 2 barcodes. Now compute the bottleneck distance between these 2 new barcodes, each one augmented with the same bar. Then you will reduce the matching distance, the bottleneck distance between these 2 new barcodes. Why? Because you have one more term to match with other terms from the other barcode. And that's the reason why you have an inequality. And this is connected to the fact that when you take a rank decomposition and then you restrict to a line, you do get a rank decomposition in 1D, but that rank decomposition may not be minimal. So you might have positive and negative bars that would cancel out in the rank for the rank invariant. But when you compute the matching using this augmented decompositions in 1D, you get more freedom to match stuff together, and so you reduce the bottleneck cost.
Thank you.
Are there other questions? Yes.
Just one stupid question. Is there any chance to go from 2 parameters to 5 parameters?
So on paper or on computer? Yeah, I think we are really focusing on the 2-parameter case now, because I mean, just think about it, like start having, simplicial complex filtered in 3 dimensions. So there's going to be a lot of simplices when we appear at incomparable indices. So in theory, there's nothing stopping you, I think, but like in practice,
The theory works in arbitrary dimensions. Eventually, it works in arbitrary dimensions.
Yes.
The problem here is that you have to compute the ranking there. The algorithm that Magnus presented actually works in arbitrary dimensions, but the complexity scales pretty badly.
well, is it here like it's O to the power 2b times n to the power 2b?
Yeah. On the other hand, if you want to store the ranking there as a function over the pairs of elements in your preset, it's actually going to be, you will need a space that will be n to the 2d already. So you can say that this algorithm is almost output sensitive, except that there's this extra factor of 2 to the 2d. So that's not that bad, but the thing is that even storing the ranking there after computation already costs. But in 3D, that should work. It's just that the implementation that we made was in 2D, made for 2D so far, but it's part of our plans to go to higher dimensions. Any more questions? Yes.
Yeah, I just had a question about the projective resolution.
Yeah.
So it's just to have an idea of how this works is, I kind of maybe can see that you, each time you're sort of removing what the last hook you made left out or something, and then filling more stuff in with new hooks at each stage, or?
Yeah, you're moving iteratively throughout the grid. That's
Yes,
just
okay. So you just look at which parts are not covered or are too
Somewhere
covered,
there.
and then you
Yeah.
add or.
It's similar to what you would do like the normal setting.
So there is some canonical way of doing. So each time.
Unique resolution, but
Yeah, yeah. Well, yes. I mean, I don't. You mean, yeah, I suppose you should be able to do it in the same way. So you just compute. You would do like the normal case, right? So you find the generators, and then you compute the kernel and take up like a free cover of that and then projective cover. You just continue. That should give you the minimal resolution. Yeah.
And then sort of with the diagrams that corresponds to just either adding or deleting certain bits. So
it's just that computing